Okay, for those of us that are not more than 50% done, what's the issue? Is it just time? Is it... Okay, so if it's time, how long? Okay, I'll turn around, in fact. If you have worked on the lab for more than 6 hours outside of the lab time, raise your hand. And then someone tell me approximately the portion. Okay. You can put your hands down. I'm going to turn around. All right. So 6 hours is still not enough time, right? But just going by the university credit policy, right? 3 hours per week per units. We have 5 units. So we're 5, aren't we? Oh no, we're 4. Lab is only 1 unit?
Yeah.
Oh, it's 2 units for us. Okay. So 4 units. So 6 hours is half of the expected time for a week of work. Right? Because 3 times 4 is?
12.
Yeah.
Yes.
So it's expected to take some time. So just don't give up on it. You should be able to finish the lab in 12 hours. I think most of you that are almost finished would agree that I gave you quite a lot of help with it in terms of like guiding you through the process. What are the different steps that you need to do? And from your knowledge of all of the previous labs, it should build up to this. So if you're still having problems and you're getting stuck, and that's what's causing you to take more time, talk to Ford, talk to Mark, ask me questions on Piazza. We won't be extending the due date of this lab, but we will most likely be accepting some later submissions with penalty. Okay? Any questions on that? All right, so this week I am not helping you with your lab in lecture. That is, this next lab is a VGA lab. Mark will help you in the lab time. It shouldn't take as long as the memory lab. Like we mentioned, memory lab was the hardest, the longest lab. But your final project looks quite a lot like the memory lab. All right. So today, I'm actually going to start talking about the final project a little bit more. So if you remember, we already talked about hyperdimensional computing, right? And we went over inference and how it works. So inference is what you are required to implement for the final project. What I'm going to cover today is encoding and training plus retraining. So if you implement any of these 3 things, each one of them can be 20% extra credits on the final project. And then the other option for extra credit on the final project is optimizing your design. So the first 2 requirements are a correct design of inference, right? So that's the baseline. If you do those 2 things, you'll get 100% on the final project technical parts. And then beyond that, you also have the presentation and the report. And then you have, you can implement encoding, you can implement initial training, you can implement retraining, and you can optimize your design. So you can do any of those 3. Each one of them would be 20% additional to final project. Great. And not just the technical parts, but 20% additional to the entirety of the final project grade. Lecture grade. So in order to help you do those parts, I'm going to cover encoding, training, retraining today. Okay. So more HDC. Here, this is encoding. Let me pull up the laser pointer. All right. So in order to do encoding of a feature vector, and a feature vector is just your input data, whatever it is. Could be images, could be like voice, like from measurement from a microphone, could be in the frequency domain, all these other things. It could be features extracted from images. But this is your general feature vector, and we're saying it has n features. In order to encode this into a hypervector with 10,000 dimensions, we are going to use these two banks of hypervectors. These banks of hypervectors are generated by the algorithm. You would not have to implement this if you wanted to implement encoding. You just need to load these hypervectors from the code into your memory. But how are these things generated? Well, this bank of hypervectors, we call them the ID hypervectors. Let me get this out of the way. Why can't I? Oh. Hello. There. All right. So these are your ID hypervectors. You generate one ID hypervector for every feature position. So if we had a 10 by 10 grayscale image, how many feature positions do we have? What are our features? In an image, what are your features? 10 by 10 image. What's an individual dot on a picture called? A pixel, right? It's 10 by 10. How many pixels are there? 100. So you would have 100 ID hypervectors, all of them randomly generated, such that they're all pairwise orthogonal. And we talked about what that means last time, right? So that means that about half of the dimensions are different between any two pair of these hypervectors. So these are used to encode the positional information of your feature vector. These are your level hypervectors. Let's go back to the 10 by 10 grayscale image. Let's say each pixel has an 8-bit value. That means the data ranges from 0 to what? 8 bits. 0 to what? How many different combinations can I represent with 8 bits?
So 48.
So that would be signed representation. We're not doing signed representation, right? Pixels don't have negative values. So it's 2 to the 8, 256. So 0 to 255. Right? So this Q, or number of level hypervectors, is arbitrary. You can select whatever you want for this number of level hypervectors, but it's going to affect your precision of encoding the feature values. So since we have, in our example of the 10 by 10 images with 0 through 255, if we make Q 256, then we have perfect precision where the first level hypervector would represent a pixel value of 0. The second would be representing a pixel value of 1. The last one would be representing a pixel value of 255. Right? But we can also choose something smaller, like say 50. And then the first level hypervector is not just representing 0, it's representing 0, 1, and 2. So any one of those pixel values would map to the same level hypervector. So you lose some precision when you're encoding, but you have less level hypervectors. Make sense? Okay, so the next thing is these are not completely randomly generated. The first one, let's just call the first one the bottom one, level hypervector representing 0, is randomly generated. The second one is a mutated version of the first one. So it's only slightly changed because 0 is close to 1, so we want them to be fairly similar, right? And then for the third one, we change the second one a little. So the third one is just as similar as the second one is similar to the first one, but the third one is more dissimilar to the first one than the second. Right? Because 3, or in this case, the third one would be representing 2. 2 is further away from 0 than 1 is, right? So it should be more dissimilar. And then by the end, when we get to the last level hypervector, the last level hypervector should be orthogonal to the first one. Okay, so we see how this is generated, why they're completely random, how this is generated, why they're not completely random. Yes? Okay. So now we can encode the feature vector. First thing we do, we get the ID hypervector representing the first position. Second thing we do, we take the value of the first pixel, so the value in the first position, look up the level hypervector that represents that value, and then we element-wise multiply the ID hypervector by that level hypervector. And what we talked about last time, this element-wise multiply is associating information. So now we're associating the first position with this feature value. Okay? ID1, this is a 10,000 dimensional vector, right? Level X, this is also a 10,000 dimensional vector, right? I element-wise multiply. What is the resulting vector size? It's not a trick question. 10,000, 10,000, element-wise multiply. So I take the first one, multiply it by the first one of the first one. That's my new first dimension. Second one times the second dimension. That's my new second dimension. Yes, so 10,000, right? So I'm still 10,000 dimensional, okay? Now I go to the second feature, get the ID hypervector. What's next? Yeah, get the level hypervector for the second feature value. And I do the same thing, associate the position with the feature value. And this again is a 10,000 dimensional vector, right? And now I'm going to element-wise add them. So element-wise adding is bundling, and bundling is memorizing. So now I'm memorizing. First feature has this level, and second feature has this level. 10,000, element-wise 10,000, my resulting vector is 10,000, right? I do this process for every single feature position. And now I have a 10,000 dimensional vector that encodes my image into hyperspace. So we see how we go from this n-dimensional feature vector to a 10,000 dimensional hypervector, right? So that is encoding. This is inference. But before we can do inference, I'll also cover initial training. We talked about it last time, but initial training is very simple. You first encode all of the samples that are cats into hypervectors, right? And now I have one hypervector representing this image of a cat, one hypervector representing this image, one representing this image, one representing this image. Now to get one overall hypervector representing cats in general, I'm going to memorize all of those cat images. Okay, and how do we memorize? The operation is right here. We element-wise add them, right? So initial training is just take all of the encoded hypervectors belonging to one class, element-wise add all of them into one hypervector. And then after you element-wise add all of them into one hypervector, if the dimension at the end was negative, make it -1. If it was 0 or positive, make it +1. And now you have this 10,000 dimensional binary pattern that represents cats. This is initial training. Initial training is simple, easy to understand. Okay. Do the same thing for dogs, right? Now I have 2 hypervectors, one for each one of my classes. For inference, I have a new image I've never seen before, right? First thing I'm going to do is encode it into a hypervector. And then I'm going to binarize it the same way that we binarize the class hypervectors. And now that we have a binary query hypervector, binary class hypervectors, my similarity check is very easy. Just count the number of matches or mismatches. If you're counting matches, take the maximum as your output class. If you're counting mismatches, take the minimum as your class. But either way, it's the same class, right? So this similarity check part is the requirements for the final project. You will be reading your application that you're working with is voice data, and it's people saying the letters of the alphabet, A, B, C, D, E, F, G, so far, and all the way to Z. So there's 26 classes. Okay. Yeah, so you can. So the first part of your lab, which you'll be doing next week as part of lab 10, is extracting the class hypervectors and the query hypervectors from the code and saving them into a new RAM file module. So you'll have 26 class hypervectors, and the dimensionality for your final project is not 10,000, it's 1,024. And you have 128 query hypervectors to print out. And then once you have that data in your RAM file, from the memory lab, we know how to read from RAM, right? We know how to create the data path, load data into the data path, create the control, and perform this similarity check. You just need to count the number of matches or count the number of mismatches. All right. right, so that's similarity check. Here is retraining. So retraining is fairly simple as well. You take the encoded samples of the training data sets. You go one at a time, use them as queries, and then do your inference with the training sample and your class hypervectors. Now, if you get a correct match, what do you think we should do? Is there anything to change about the model if it's correct? No. You do nothing. Okay. Now, if we do our similarity check and we get an incorrect match, in this case, we're saying that we incorrectly classified the query as class 2, but it actually belonged to class 4. What we do is we subtract the query from class 2 to make it less similar to the query, right? It's kind of like removing information. And then we add the query to class 4 to make it more similar to the query. And over time, as we update these class hypervectors in this way, the next time we see this query, we should eventually get it correct. And this is retraining. But we already talked about how we have quantized values, right? Our class hypervectors are not integer values. They're binary values, right? After we did the initial training, if it was negative, we made it -1. If it was positive or 0, we made it +1. So if we directly do this subtraction to our quantized vectors, it will change our model significantly every single time we do this addition and subtraction. So in order to update the quantized model, our retraining is a little bit different. So we do our query. The query is checked with the quantized model because that's what we're going to use in the end, right? If we have a correct match, again, nothing to do. But if we have this incorrect match, rather than updating the quantized hypervectors directly, we keep the integer hypervectors for retraining around. So the result of the element-wise addition of all of the samples is this integer hypervector. We do the subtraction and the addition to the integer model. And then we re-quantize the integer model and only update the dimensions of the class hypervectors if the sign was changed by these updates. And again, over time, we might have to retrain with the same query multiple times, but it will change these patterns to more accurately identify our classes. Okay. So now we know how to do encoding, right? How to go from the n-dimensional feature vector to this d-dimensional hypervector. We know initial training. How do you do initial training? Element-wise, add all of them together, belonging to the same class. We know how to do inference. This is the second time we're covering inference, right? And inference is your requirement. Okay. So is anyone still confused about how inference is performed? We all understand? This is your final project. And then retraining. Also fairly easy to understand, right? If you're right, do nothing. If you're wrong, update it in this way. Subtract the query from the incorrect one, add it to the correct class that you should have chosen. Okay. So that is the last of hyperdimensional computing tutorial that I'm going to give. Both of these lectures were recorded, so if you forget anything or you need a reference on how these different operations occur in HD computing, you have the recorded lectures. Right? Your code for today before you go is 390.
The lab 10, we had to learn Python.
Lab 10, you will just be printing with Python. All you have to do is print values out. You are not heavily modifying the code at all. You are only printing values out. Okay?
You're not storing them, or you're just printing them out.
You're printing them out so that you can then paste them into the RAM VHD file. And I will talk more about that on Friday. And I'll tell you exactly where to go into the code, exactly where it is that these class hypervectors are, where they're looped through, as well as where the query hypervectors loop through. And all you have to do, again, is print. You just need to loop through the hypervectors, print them out. 390. 390. Okay. So this is it for today. I have office hours. And I'll also stick around if you have any questions. You have the memory lab due today.
So inference, you're taking query sample and relating it to whatever it's coding and adding together.